Okay, good afternoon and welcome for this parallel session on opinion dynamics. I have 6 talks in schedule, so we start with the first one with Nada Ghanem, who will talk about some fine problems in online recommendations tackled with agent-based modeling. So Nada, please show your title, exact title, and start your file.
Okay.
Can't see anything.
Presentation is a
no. This is not
supervisors. Dietmar. Hello everyone.
So,
can you hear me now? PhD student. Can you hear me now?
No, but we don't see your slides. You know. You see the screen?
Yeah, I share the screen.
Your directory, only your directory.
Okay, now.
And now it's better.
Now it's okay.
Okay. Okay. Go on.
Okay. At the University of Klagenfurt. This presentation is a work under progress with my supervisors, Dietmar and Stephan Leitner. The title is Investigating Longitudinal Effects of Online Recommendations with Agent-Based Simulation. Many of us are familiar with websites such as Amazon, Netflix, eBay, and many more. These websites employ recommender systems to suggest useful items for the end users. The idea of a recommender system is as follows. Users enter into the website and interact by browsing, searching for items or consuming, reviewing, and then the recommender system learns from these interactions and extract preferences. The preferences for users are used to generate recommendations. Next time the users enter to the website can see a list of recommended items and can do further decisions. And then also can send feedback to the platform, to the recommender to update the preferences data. Most of the literature about the recommender systems focus on optimizing for the end users when designing a recommender system. It turns out only concentrating on the utility of the end users may lack the exploration of other aspects of the system, particularly if the system runs within a multi-sided platform. Multi-sided platforms add value for multiple stakeholders, each with different objectives. And keep in mind, their objectives may conflict. As you can see here, an example of a multi-sided platform, Airbnb, with multiple stakeholders. In our work, we will have 2 possible conflicting objectives: maximizing the utility of the consumers and maximizing the utility of the platform provider. We aim in this research to investigate the impact of different recommendation strategies on stakeholders' objectives. We want to see how consumers' trust is adapting over time, the trust of consumers towards the platform provider, and also we want to see how does the total profit of the platform provider evolve. As a research methods, we use agent-based modeling to simulate this phenomena, and we initialize the model using a real data set called movie lens data set. This movie lens data set contains ratings for around 9,000 movies of 600 users. Before we build the model, we have some expectations. We expect that if the recommendations are more towards maximizing the utility of consumers, this will lead to higher trust and higher consumption. And if the recommendations are more towards increasing the provider's utility or profit, that will lead to lower trust and lower consumption. So here is the flowchart of the model. We have three parts. So you can see here we have recommender system, platform provider, and consumers. The platform provider at the beginning, when the simulation starts, provide recommendations. But before that, the platform provider runs recommender system software to predict utilities or rating for consumers of unconsumed items. And then the platform provider can apply a strategy to re-rank these items based on strategy. So we have two strategies in this simulation. The first one is platform provider recommend items that maximizes the utility of the end user or the utility of consumers. The other strategy is to recommend the items that balancing between profitable items and high utility items for the consumers. And then the platform provider provides recommendations for each consumer. The consumer then make a consumption decision, and then after the consumption, consumer compute the trust and also send feedback to the platform provider. The platform provider compute the total profit and also update the ratings data. This will continue until the end of the simulation. We have several assumptions in this model. The first one, we have two types of stakeholders: one platform provider and several consumers, many consumers. Consumers can only see items through the platform provider, items that are recommended by platform provider, and can only consume one item at a time. And consumers are satisfied if the utility of the selected item is equal or above a certain threshold, which is adapted over time for each consumer. And also we assume that the consumption probability of consumers depends on their previous experiences with the platform provider, and which are represented by trust. The provider's total profit is computed each time step by summing up the profit of consumed items. And each item has a profit value that is drawn from normal distribution equal to 2 and standard deviation of 1. The upper boundary is 5 and the lower boundary is 0. As preliminary results, what you see here are the first results when the platform provider apply a strategy that maximizes the utility of the consumers. So we call this strategy consumer-centric strategy. And yeah, as you can see here, we have two figures. The figure one shows the average consumer's trust over time of 20 iterations. So the x-axis represents time and the y-axis represents trust. In the other figure, we have this for total profit over time. The x-axis represents time and the y-axis represents total profit. The trust in figure 1 of this strategy grows up and it's higher. It seems that most of consumers are satisfied when the platform provider recommend items that maximizes their utilities. In the other side, the total profit increases in this strategy, but because it starts from 0, but then it stabilizes as this strategy doesn't include the profit. These results here, there is another strategy in the red line. So here we call this strategy consumer provider balancing strategy. The platform provider in this strategy recommend items that recommend items that balancing between profitable items and items that maximizes users' utilities. So here the trust in figure 3 of the red line of this strategy, new strategy, is lower than the previous strategy. And the reason behind this, because here recommending profitable items might not be satisfiable for all consumers. And so that's why the trust stabilizes in this strategy. In the other side, as you can see, the total profit of this strategy is higher than the previous one. So this means that the platform provider is satisfied somehow because the total profit is increasing. But then, as you can see, there is a slight decrease over time of the profitable items, because here in the simulation, in our simulation, we have only items that number of items are not changed over time. So the platform provider doesn't add new items over time. So the system runs out of profitable items. As a conclusion, the simulation confirms that different recommendation strategies lead to different impact on stakeholders' objectives. And consumers' trust is higher when the platform provider recommend items that maximizes their utility, or as we call it, consumer-centric strategy, and lower if the platform provider recommend items to balancing between consumers' utilities and also platform providers' utility. For the next step, we will add social media in this model. So it will be interesting to know how social media affect the consumption and also the stakeholders' objectives. We will add new items to the items catalog over time, so we can see more dynamics by adding new items, and this is match reality, real system, so a platform provider add items over time. And we will also run sensitivity analysis. Sensitivity analysis will help us to understand how different combinations of variables can affect the dynamics of the model. Thank you so much. And if you have any question, please feel free to ask. Thank you.
Okay, thank you, Nada. And we have time for questions, just 2 minutes left. So somebody has question? Or may I start with just asking you, what drives this system? How do you create your consumers? Is there some kind of social dynamics behind it, or you just introduce them by randomly or something?
Yeah, so the consumers are taken from data. So I have already a data set.
Data with the time scales, or?
You just data of ratings from consumers so it's called movie lens data set. So we use this data set, so they gather ratings for movies from users, from real users. So yeah, I use this data to like.
You have a timestamp also for the activity, okay?
No, I don't have.
No, just the order, just.
Yeah, I don't have much details about consumers.
And what's time in your simulations? You had time. Is it just number of actions, or?
Yes, yeah. So it's days. I consider it as days here.
Days.
Mm-hmm.
Okay. How you introduce days? Actually, time scaled here.
No, this is just.
You think it is days, but
yeah.
It's number.
Yeah, but it's not taken from data itself. Yeah.
Okay, from data. Right.
Mm-hmm.
So, some more questions? Does somebody has question? It doesn't seem so. I don't see anyone. So, if not, then thank you. There's a chat. How would you introduce social media? This is the question. Question on the chat. Okay, can you answer that?
Yeah. So we'll think about like connecting consumers together through social network.
Mm-hmm.
And then we will see how, for example, how the consumption for these consumers are affected by others' decisions.
Also using data probably.
Yeah, so we are studying the model in both sides from platform provider perspectives and also from consumers' perspective. We're trying different strategies and see how these strategies affect the consumers. And I think social media will have an impact of this.
Okay, I guess this is it. Okay, I think we stop with this first presentation. Thank you very much, Nanda.
Thank you.
And we move to the, please stop sharing screen. And then we have next presentation by Maria Castaldo.
Yes.
Maria Castaldo, okay. You start sharing your screen. Maria will speak about some dynamical problems of attention online.
Yes.
So
I pre-recorded.
this is much more precise title. So please.
Yes. Okay.
My name is Maria Castaldo. I am a PhD student at CNRS in France, and I'm going to present a work done in collaboration with Tommaso Venturini, Paolo Frasca, and Floriana Gargiulo. As you're going to see throughout the presentation, the results that I'm going to present are the outcome of a strongly interdisciplinary collaboration that included sociology in a specific field of digital methods, computational social science, and mathematical modeling. The research question we are going to address is how to model online attention regimes in relation to recommender systems. For those of you who are not familiar with the concept of recommender system, they are tools that sort and organize content online in order to meet our interests. So for example, when we Google for a certain topic, web pages are sorted by relevance to that topic, but also in order to meet our personal interests. Same thing happens when we open our own page on social networks. To address this question, we started from a very influential article written by Ghanem and Bosch in 1988. In this article, they presented a model called the public arena model, in which they were describing an attention economy mainly based on traditional media, and therefore televisions and newspapers. Even if right now we are dealing with completely different social media online, we claim that some of the hypotheses that the authors did in 1988 are still valid even in our context. And that is why we decided to give the public arena model a mathematical formalization in order to be able in the future to compare it with evidence coming from data. It's therefore important to understand which definitions and which hypotheses of the public arena model we kept in our formalization. The first and most important definition is the one of matter of attention. Matters of attention are the objects that are capable of gaining attention. So they could be, for example, tweets in Twitter, they could be videos on YouTube, or they could be articles of an online newspaper. Another important concept is the one of arenas. Arenas are the environment in which attention matters live. And they could be platforms, they could be subparts of platforms related to a specific topic. Let's now focus on the hypothesis of the public arena model that we kept in our formalization. The first and most important one is the one related to the fixed attention capacity of arenas. Ghanem and Bosch sustained that on each arena there was always a fixed attention that attention matters were sharing. This was the outcome, this was the effect of the limited amount of time that each user can dedicate to information every day. As attention becomes limited, attention matters have to compete in order to gain it and to reach the widest public possible. In their model, there was also included a way to consider exogenous influence for external events. And at the same time, there was a mechanism that was pricing popularity with some more popularity. In our case, we we can interpret this mechanism as the effect of a recommender system. So we model the recommender system as tools, as algorithms that reward trendiness. And by trendiness, we mean the speed with which a certain item gains popularity. We formalize these dynamics through a discrete time model. Let's consider an arena with a maximum number of items equal to n. We can then define a potential visibility of an item I at a certain time step as the sum of its previous visibility plus its previous variation in visibility multiplied by a parameter alpha. On top of that, we can add an exogenous noise, which is modeled through a random variable with a normal distribution and mean equal to 0 and standard deviation controlled by a parameter c. As we can notice, this potential visibility might have negative values in the case in which exogenous noise is negative and bigger than the rest of the equation. In that case, in order for visibility to make sense, we should set those negative values to 0. At the same time, to meet the constraint of the fixed attention over our arena, at each time step, we need to normalize this potential visibility in order to get the real visibility. By doing so, we grant the sum of the visibility of the item over the arena to be always equal to 1 at each time step. One of the strengths of this model is that it needs very few parameters. The most important one is alpha. Alpha models the importance that is given to trendiness in different arenas, and therefore is our way to represent recommender systems. To understand the role of these parameters in our model, we simulated the dynamic for different values of alpha. What you see in the slides are different arenas where different values, different weight is given to trendiness. In all these arenas, the overall attention is fixed and it's equal to 1, and different attention matters, which are colored in different way, share this attention along time, which is represented by the horizontal axis. As we can see, when alpha is equal to 0, and therefore when no weight is given to trendiness, attention matter keep the same amount of share they had in the very beginning along the whole time, with a small exception of some noise given by exogenous factors. Once we increase the value of alpha, we see that attention matters stays in the public attention for a shorter amount of time. As a consequence, attention matter follows each other faster, giving rise to an accelerated public debate. Let's have a look more in detail at life cycle duration of our attention matters. We define the life cycle as the time in which an attention matter is capable of capturing attention. As we can see, by increasing the value of alpha, and therefore by increasing the weight given to trendiness in a certain platform, the average life cycle duration decreases, no matter of the number of attention matters we have in our arena. Let's have a look at some other quantities that are important for our simulation. One of these quantities is the maximum peak of attention. The maximum peak of attention can be defined as the maximum share of attention obtained by a certain item at a certain time step. As we can see, by growing the value of alpha, also the height of those peaks increases. This result suggests that at every time step, few items are going to share the overall attention. That is why it's interesting to analyze the behavior of some concentration index like the Gini index. As we can see from the second plot in the slide, by increasing the value of alpha, also the concentration of attention at each time step increases. Therefore, at each time step, we are going to have few attention matters which collect the overall attention. We can conclude from these two plots that increasing the value given to trendiness in arenas, we compromise the richness of the public debate. we define the attention regime resulting from a high value of alpha as junk news bubbles. Junk news bubbles are a situation in which a large share of public attention is attracted by content that is not capable of sustaining it for a long time. Once we formalize the attention model, we try to find in online social media the evidence of different attention regimes. To do so, we started collecting data of temporal evolution of engagement metrics on YouTube. In particular, for a corpus of around 100,000 videos, we collected the evolution of views hour by hour. The selected videos consist of all the video published after December 2019 by a list of 1,000 channels in France dealing with politics and news disclosure. It is important to stress the relevance of this dataset as it cannot be directly obtained from the YouTube API, which is the tool researchers and developers use to retrieve data from YouTube. We then try to understand whether different channels had different regimes of news consumption. For each channel, we therefore evaluated the same metrics that we studied in our model, and therefore life cycle and concentration of attention. We define the life cycle of a video as the time it takes to collect the 85% of its total views. At the same time, we define the concentration of attention in a channel as the Gini index of the distribution of views among different videos. As we can see from the plot, the two quantities seem to be related. Highly concentrated channels show to have videos with a shorter life cycle, while channels in which the attention is shared more equally between videos have content that lasts longer in the public debate. This plot suggests other interesting results. Traditional newspapers, like France Culture, are positioned in the top left part, with long life cycle and low concentration. On the other hand, channels known for publishing junk and fake news content, like Sputnik France, seem to be located in the bottom right part. This might suggest that certain type of attention regimes might be associated to different type of content. Therefore, the link between our formalization and empirical evidence seems to be promising and will be surely object of further studies. Thank you very much for your attention.
Okay, thank you very much. We have time for questions.
Yes.
Yeah, go on. Who was asking? How we no, okay, there is no, this is previous chat. I don't see the chats. Okay, can I just ask you before somebody types? I think somebody is typing. So you say that there's a finite lifetime of any matter of attention, right? Which is a very good message. Now, is it basically due to this crowdedness on the platform and finite capacity of the recommending system or so, or it is also a matter of the contents of that matter itself? Okay. Mm-hmm. Actually, in the model, you don't have the contents, but I think you train your model on some kind of real data where this should matter, right?
Yes, absolutely. Actually, the data we used were data on channels that were dealing with politics and news. So this kind of content actually always ends at a certain point. So videos just, most of the time videos are watched just for 7 days, just to give you an idea. So I won't say that this short life cycle could be applied to any kind of content on YouTube, because, for example, music has got a completely different economy of attention. But for what is related with the information, the evidence shows very, very short life cycles.
Sure, that's really nice. Very nice message. Okay, there's another question on chat. How does do you see that?
Yeah.
Okay, read it and then.
Okay. How does the dynamic of your model change if you have no exogenous factors?
Or put it another way, does noise drive any cyclicity? You understand the question, right?
Yes. Actually, we were in a situation in which noise was not that relevant. What we were modeling were not external shocks. Of course, our model is not capable of predicting what happens online in the case of a shock like COVID or a shock, let's say, that lasts long in time. Our exogenous noise is just a random noise, which at every time step is a random variable with mean equal to 0. So it has not a strong effect, I would say.
I guess this is the answer, and we have to move on. Thank you very much once again. Please stop sharing. And we move to the next presentation by Felix Gaisbauer.
Yeah. Can you see my screen?
Yeah.
Perfect.
So Felix is talking about the quantifying willingness in public opinion. Okay, please go on.
Exactly. Thank you very much. This is work I carried out together with my colleagues Armin, Pournaki, Sven, Banisch, and Eckehard, Olbrich. And I will talk about the modeling of willingness of public opinion expression first, and then hopefully I will have a little bit of time talking about the observation. I hope that this will also retrospectively a bit motivate the modeling further. So I start off with a very simple model idea, which has been largely overlooked in opinion dynamics, namely that opinion exchange between individuals can affect how willing they are to express their opinion publicly in the future. And this has some theoretical grounding in a sense, namely Elisabeth Noelle-Neumann's spiral of silence. In her theory of public opinion, Noelle-Neumann states that people constantly and mostly subconsciously monitor their opinion environment. And in case they realize that they hold an opinion that differs from their impression of the majority opinion, especially for controversial topics, they tend to be less willing to express their opinion publicly any longer. And this might set into motion some kind of spiraling process where one opinion fraction gets more and more vocal while the other one might become more and more silent. So this was the premise to our model in the sense, and for simplicity, we let it take place on a very simple interaction network structure with two fixed opinion groups. So their opinion will not change throughout the whole model. And these two groups form two blocks in a stochastic block network that you can see here. And with this, we can already define, because the groups can have different sizes also, we can already define two parameters that will guide us through this model and that are therefore very important. The ratios of the expected in-group to the out-group connections for each opinion group, called gamma for opinion group 1 and delta for the second opinion group. And they are simply given by the product of the ratio of the group sizes times the ratio of the in-group versus cross-group connection probabilities. And what do those mean? Well, a gamma or a delta bigger than 1 means that agents of the opinion group on average have more connections to others that hold the same opinion, while smaller than 1 means exactly the opposite. And on this network structure, we then define what we call a so-called silence game. So there are simply two possible actions for each agent: silence or the expression of opinion. And expression comes at a certain cost. C, you may think here of the effort of typing in a reply on social media or joining a demonstration. And then agents act according to the perceived opinion proportions in their opinion environment. So if it appears to them that they hold a minority opinion, they will choose silence. And otherwise, if also the costs are accounted for by this majority, they might choose opinion expression. And now we come to the whole point of this model, namely that the impression of the opinion landscape of these agents is shaped only by the expressive agents. After all, the opinion of silent agents is not public, so how should I know what opinion they have? And therefore, this will be like the crucial point of this model. And with this, we can already look at the Nash equilibria of this silence game. So you see here that in the Nash equilibria, it turns out, because the network structure is within the groups quite homogeneous, that the opinion groups act uniformly in the equilibria. So here opinion group 1 and here opinion group 2 have the same collective action. And you see gamma and delta here again. So if gamma and delta are very small, below this threshold here, then we have an equilibrium where no one speaks out, because people are effectively only connected to people that they disagree with. So we have no incentive of making their opinion public. But if you increase, for example, gamma here, which can happen if the group size is fixed by increasing internal cohesion, so internal connections, then you get into a region where you get a Nash equilibrium where the group expresses itself. Or if you increase both gamma and delta according to some homophily principles, so more internal connections, then you get into a region where either group 1 speaks out or group 2, or there is complete silence, but not both at the same time. And if you increase gamma and delta even more above this threshold, you get into a coexistence region where also a Nash equilibrium is possible, where both opinion groups express their opinion publicly. So this is quite the basic setup here. The problem is that this doesn't tell us anything about equilibrium selection, about issues of bounded rationality, and so on. So what we also did was we made a dynamical formulation of this with the help of the reinforcement algorithm, learning algorithm of Q-learning, where agents learn the expected reward for opinion expression upon feedback by a random neighbor. According to this equation here, the rewards are given by these 3 options for opinion expression, and alpha is the learning rate. And what is important there is also that we chose the Boltzmann action selection mechanism on the decision of whether an agent expresses itself or not. So if this Q value is below 0, this means that most of the time the agent will be silent. And if it is above 0, then most of the time the agent will express itself. And if we then average over the Q values of the respective opinion groups, so we only have 2 Q values anymore, the average of each group, and then we go to continuous Q learning equation, we end up in a 2-dimensional system of dynamical equations, some sort of mean field approximation, if you will. And with this, we can do some bifurcation analysis of this whole system. So now we can look at the fixed points and how they change if we change certain parameters. And there are many of them, but I will show 2 bifurcations now that I find interesting. The first one is internal cohesion. So if we assume that beta, delta, and the costs are fixed, and only the gamma is changed, and we assume that this opinion group 1 is a very small minority and also internally not very well connected, then they will start off here with a very low value of gamma, where they have a Q1 that is very negative, so the group is mostly silent. While the second opinion group, the colors correspond here, is loud. And if you increase gamma now by internal cohesion, so increase the internal cohesion of the minority, a fixed point pops up where the opinion group becomes expressive while the second opinion group is silent. And if you tune the internal cohesion even more, the fixed point where the second opinion group is expressive disappears even. So more internal cohesion can make even a minority gain public audibility. And if you look at the costs for expression and make them asymmetric, so the costs of one opinion group are different from the costs for expression of the other, then a good example for this is if you have a society where certain demographic groups might not be able to express themselves on social media, but social media is very important for deliberation, so they have higher costs of expression. So they start off at a very high cost here, while the other group has cost 0.1, then they are effectively silenced. And if you decrease the costs here, fixed points pop up where this group is expressive, and so one where the group is expressive alone, and the other one is a coexistence fixed point here where both groups speak out. And if you have even negative costs, so the group is then encouraged to voice their opinion, then this fixed point disappears where this group one is effectively silenced. So that much from the modeling side. I could go a bit more into detail now, but I also want to talk a bit about observing this willingness of opinion expression, especially online, in the last 3 minutes of my talk. And this poses some difficulty, because how should I measure in online data interaction that is not there? How should I measure silence? And we kind of found a method to at least get a bit at this for Twitter data. So here you have a retweet network of the Saxon state election last year, so elections in Germany. And you see here that this is a polarized retweet network. This is a force-directed layout. And we classified the force-directed layout of the network into 3 opinion clusters. Here we have a left-leaning majority. Here we have like a center-right in between region. And then we have here another pole, a kind of minority pole, where mainly far-right politicians and parties can be found. If you have a question about this later on, I can go a bit into detail about force-directed layouts. But the essence here is that retweeting on Twitter is not really something that is risky. It's not as risky as opinion expression, because only your followers can see it, and you cannot reply to the retweet. If you reply to this, then the reply is to the original tweeter. And therefore, this is kind of our background distribution for the opinions in there. But what is more risky on Twitter and what comes close to opinion expression is engaging in debate. So replying to other users, discussing with them. And with this background information here of the opinion distribution, if you may, we checked who of these users is actually engaging in debate. And I will now blur out all the users that are not engaged in debate. And all of a sudden you see this majority doesn't really look that much like a majority anymore. And so you can see the differences here in willingness of opinion expression. You can also quantify this. We did this with the election data set and also another one, where you see that this far-right cluster was double as, was like the left cluster was only half as probable to get involved in the debate than the far-right cluster, which resulted in a lot of visibility for this cluster. And I think I'm already at the end of my time. But with this, I want to conclude there is a bit more to this. We also went into the structure of this debate for these 2 case studies that we had. So if you want to take a look, the modeling paper was recently published in PRE, and the other paper is under review, but a preprint is already online. I can also share it in the chat. And thank you for your attention, and I'm happy to take additional questions.
Okay, thank you, Felix. We have time, a couple of minutes for questions. Questions, please. Okay, can I put first question before somebody types? I think. Okay, you mentioned that this is on the network. You have some kind of relationship between the agents in this process, right? So, and you consider this a block model as a typical social graph, right? Yes. You mentioned that in the abstract, but if you do simulations, for instance, you can vary the network properties much more and see how this impacts this process, because it seems very much very unstable if you change these parameters gamma so freely. I guess this parameter can be somehow related to the network structure as well, right?
Yes. So I would say, I mean, the stochastic block model was good because we could do some analytic things with this.
Yeah, that's right. And this is typical social graph, right? Actually.
Exactly. So I mean, there are good models of homophilous networks that have different blocks of opinion, but internally also some kind of preferential attachment. mechanism. I think there was a paper by Li and Karimi recently. They had a good generative model of this, and also others. And yeah, so simulatively, I would also be interested in furthering this. So this would be a bit further work for the model. With that, you're right. But analytically, we were also quite happy already to.
Yeah, that's very nice. That part is very nice too for understanding the mathematics. Definitely. Yeah. Okay, thank you.
Thank you.
Great. Could you send us the link of the papers? Please send the link of your paper on chats.
Yes, I will do it in a second.
Please do. Okay, thank you. We can now move to next talk.
Okay, I will stop the sharing.
Hello, do you hear me?
Just a moment, just.
Okay.
Okay, you're Jannach, right?
No, I'm Simone Lackner. It was not clear which of the two of us will give the talk.
Oh, okay,
but,
okay.
It will be me after all.
You are co-author, right?
Yes, exactly.
Okay,
Joanna is the group
yeah,
leader.
that's great.
I'm not sure, Basilica, is somebody else giving the next talk?
Yeah. No, it's co-author of the same abstract.
So I should
Co-author,
shift.
Okay,
just a minute.
Yeah.
Give me a second.
So this is Simone Lackner, but she already appeared.
Yeah, give me a
Yes,
second.
I'm here.
Do you have
Okay,
this?
you're all set. I made you a co-host. Yeah.
Okay, so now I can share my screen.
Now you can share your screen, okay? So Simone,
So do you see my screen?
Yeah, just a moment. And we'll talk about negative attitudes from lots of knowledge or lots of information. Okay.
Okay, thank you. Okay, hello everyone. My name is Simone Lackner, and I'm presenting work that has been done in collaboration with Frederico Francisco and Joana Gonçalves-Sá, who is the head of the Social Physics and Complexity Group at LIP in Portugal. And I will tell you now why we think giving a little knowledge could be a dangerous thing. So our project started from the observation that people tend to share information they don't really understand. So this is a particular famous tweet from one person, but it's not unique to this person. We could see this all over the net, and we can still see very similar phenomena. That was at the beginning of the pandemic, where people detected that their bleach or disinfectant protected or could kill the coronavirus. And for the majority of the population that never have heard about the coronavirus before, this was a strong evidence that definitely it must be a conspiracy by the government, because how could it be that the producers of bleach and disinfectant did know about the coronavirus when I didn't know about it? And they even broadened that more than I from, we don't know nothing about this. And of course, a fast Google or Wikipedia search would have made people realize that coronaviruses are around for thousands of years, that there's also lots of research done on coronavirus, and that this one in particular we're dealing with is a new form from a vast family. But in order to go on Google or Wikipedia to search, people need to realize that they don't know. So they need to admit a gap in knowledge instead of jumping into the social network and starting these conspiracy theories. So it's like we have a gap between how much we know and how much we think we know. And although people tend to appreciate science, we'll have an issue in the near future when people have to decide if they get vaccinated or not. And we can see two paradoxes. One paradox is that for quite some time, we thought offering information will be helpful to people to make better and informed decisions. So there were lots of science communication done since many, many years. And the expectation was the more people will know science, the more they will love science. And so the more we give information, the more people will be knowledgeable, and then they will have better attitudes towards science or towards getting a vaccine, for example. But what we know now is that this is not the case. And we do not have this very linear positive relationship. We rather have sometimes a no relationship at all, or even an inverted, so a more negative relationship. So the second paradox is also that giving more information might make attitudes even worse. Namely, when issues become very controversial, people might polarize even more and their trust drops. So in this case here, only 19% of the general US population stated that scientists understand the health effects of eating genetically modified food very well. So our project started with this observation of a relationship where people don't have necessarily a lot of knowledge, possibly overestimating how much knowledge they have. And one of our hypotheses is that this might be one of the reasons why people share fake news. So we are thinking about, why do people share fake news? What modulates attitudes toward science? And what is the role of confidence? Going back to this linear relationship, but in a bit more different context, the idea is how much you know should be linear correlated with how much you think you know. So if you know a lot, you have accordingly a lot confidence. And if you know very, very little or nothing, you have no confidence. But what if in reality, it's not like that? What if confidence grows much faster, here in green, than knowledge? Namely, how much we think we know is much higher than what we actually know. And this would lead to a gap, which is a confidence gap, where we think it is where people are most susceptible to spread fake news. And that's where people might think they know what's going on with coronavirus, and where they think if the producers of the bleach already knew about coronavirus before me, then that must be a government conspiracy. So what we came up with, and this is part of a bigger project that is undertaken in the scope of a big ERC-funded project in Joanna's group, we created this indirect measure of confidence that we call here INCON, that we can apply to most tests or surveys that have any kind of knowledge question that can be answered with true, false, don't know. And so, for example, if you have to answer a question, if it's true or false, like, is an atom bigger than an electron? As a rational agent, you either know the answer, or if not, you should say, I don't know. So that you stay on this blue line where knowledge and confidence grows linearly. But if I'm finding myself above the line, so in this zone or here on the green line, it is because I got some of the questions incorrect. So my confidence is higher than my actual knowledge. So if I were to plot the ratio of incorrect, don't know answers at the same knowledge level where answer at random, incorrect, or don't know, I would have a 50-50 ratio between incorrect and don't know, answering at random. But if I have an internal bias, I maybe say more often don't know or get them more often incorrect. But how does such a plot describe the relationship between knowledge and confidence looks in reality? So together with Frederico, we looked at 3 independent surveys with a large number of participants over several years across different European countries and the US. And we had different knowledge questions with different options, either with true, false, don't know, or 3 options to choose from which is the correct one with the don't know analog of not sure. And again, as in this simulation here, we are looking at the ratios of don't knows to incorrect answers at the different knowledge level to see if we can detect the confidence gap. And so what we found in these 3 surveys, no matter at which survey we have been looking at, we find this inverted U-curve here in green, which people tend to say more don't know at the extremes. So meaning at very little knowledge or at very high knowledge, and guess wrong a lot more at the intermediate knowledge level. So we have a much bigger confidence gap here at the intermediate knowledge level than at the extremes of no or high knowledge. And we put this in a very simple model where we started with our linear relationship between how much one knows, knowledge, and how positive the attitudes are towards science. And then we included our model of the fitted data, how much people guess wrong their knowledge. And the product of these 2 gives us the inverted U-curve. And in fact, when we went back to our original data set from the Eurobarometer, looking at the relationship of knowledge, confidence, and attitude, we can see this inverted curve for statements such as, because of their knowledge, scientific researchers have a power that makes them dangerous. So we can see that people tend to agree with this statement at the intermediate knowledge than rather at the extreme of no or high knowledge. So it's a mixture of how much one knows, the knowledge, and how much one thinks one knows, the confidence, that can predict the attitudes towards science. So that's why we want to convince you that giving a little knowledge could be a dangerous thing, because it can have a very serious consequence, and we are concerned particularly about the ongoing discussions that are also now reoccurring, especially now during the pandemic, regarding the safety of vaccines. So we can imagine that the anti-vaxxers mostly fall into the group of intermediate knowledge. They know little, they consider themselves experts, and the confidence is much higher than their level of knowledge. And our hypothesis is that they will be much more susceptible to targeted fake news and negative attitudes toward science. Thank you for listening, and I'm looking forward to questions.
So thank you very much. We have several minutes for questions, and I think there should be some questions in the audience. This interesting subject. Everybody has opinion on this, right?
Yes.
So let me just put a very simple question to start with before somebody else jumps in by chat or so. You're talking about knowledge as something well known, well defined, but we know as scientists that there's a quality of information in every knowledge, okay?
Yeah.
So does this, as you say, this intermediate level, you know, half know, half confident, half know, half confident, to know actually belong to there that people cannot grasp the content of that knowledge, which is, for instance, about this vaccine. Let's put it more precisely.
Yeah, I think this is a very important question. We also are ongoing discussing, and it's difficult, I think, to grasp because, like in this service, general textbook knowledge was questioned. It's like this usual sentence, like I said, an atom is bigger than an electron.
Yeah, right. I know.
Statements, right?
To be clear, okay.
Yeah.
To be clear, but we are talking about practice. If you want to put your research to more practical thing, like about this vaccine, for instance, which actually nobody knows everything, but somebody believes, somebody doesn't. And is this actually matter of, are we capable to know what we are talking about? And then
we as scientists, or we as a population?
Also scientists, if you are not specialists for medicine, for let's say it's much closer to scientists than, you know, general population, okay? And
yeah, it's very difficult. I think, like from a population point of view, and that is what we are mainly concerned with, how people form their opinion about a given topic. Like, for example, now in the pandemic, we clearly have these discussions of wearing a mask or not wearing a mask. Maybe in different countries, the discussions are different. Or I think the mask is actually a very simple example, maybe, because there were tests and there was science done, and then there are facts and they have to be reported. But if they don't reach the people, and or let's say it better that way, every individual has a different set of knowledge, right? That depends on what opinions they are exposed to. And social networks are over amplifying wrong or misinformation, in that sense that even these anti-vaxxers, for example, could be very well informed, but they just have simply the wrong information, because also based on the confirmation bias, that when you go on Google and you search about like autism related to vaccines, depending on your previous Google search, you will find all the information that just supports your idea that you have. So it's very difficult.
Yeah, in this context, you can say mostly people hear about this scientific achievements from journalists, you know, from TV or from social media, and so that's a problem, because how you perceive something, what was translated to you is somebody who is not knowledgeable about, okay? And and these are, you know, just few lines or something. So it's about how we perceive the truth which is behind that knowledge. Okay. So are there more questions? Yeah. No, it seems not. If you have
I would have a quick remark, if I may.
Okay.
It's probably easier to say it than to write it in the chat.
Yeah, sure. Okay.
Because I don't know if you're aware of this, but there is a book by Wolfgang Schweiger, where he is also trying to get at in general, it's called the disinformed citizen or something, the desinformierte Bürger, I think it was.
Okay.
And there he is also looking at the news consumption by differently educated people. So he makes a distinction in 3 parts: the lower, the middle, and the higher educated. And he also finds that the middle educated are the ones that are excessively, compared to the others, consuming news on social media, and are therefore a lot more, this is a lot more problematic because the perception biases and all these confirmation bias and so on might hit them harder than the ones that do not at all consume news, or the ones that consume news in other paths. So this seems quite fitting, because I didn't hear whether there is also like an explanation for this Dunning-Kruger effect. The Dunning-Kruger effect, there are probably very many, but this is one that might especially be relevant in times of social media, in a sense, so that this group is also consuming news in a way that is very problematic in that sense.
Critical.
Yeah, that is basically exactly what we want to get down to. So now we basically have this indirect measure that didn't exist before. The Dunning-Kruger effect is described for many years now and ongoing up, but we came up with this indirect measure of using the don't know and wrong answer ratio as an indirect confidence. And we are now in trying to look more into detail. Who are these people? Who are this group of people? What kind of particularities do they have? And also in the near future, with the greater ERC funded project, we will look how on individual level that will lead to choosing to forward fake news or spreading it. And yeah, the book you recommended is from Wolfgang Schreiber.
I can just write the name.
Yes, please. Sounds very interesting. Yeah.
And, yes, thank you very much. I have to stop this interesting discussion. Probably you have a lot to do more.
Thank you very much.
This. Okay, thank you. And we move to the next talk. Next talk by Jingmeng Cui.
Hello, can you hear me?
Yeah, hi.
Hello.
And you speak about dynamics of panic disorder.
Yeah.
Can you start sharing your screen, please?
Yeah, let me try this. Can you see this?
Yeah.
Yeah, okay.
Okay, great.
See.
Go on.
Okay, I'll start. Hello, everyone. Welcome to this presentation. My name is Jingmeng Cui, and I'm now a research master student at Behavioral Science Institute, Radboud University. Today, I'm very happy to be here to share with you our first results of our research project from metaphor to computation, constructing the potential landscape for the dynamics of panic disorder. Human psychology is a very complex system. That means even for a very small phenomena, there is a lot of things going on behind it in a complex and dynamic way. And these complex interactions make psychological phenomena extremely difficult to explain and predict. Traditionally, psychologists usually use verbal theories to describe the interactions of the elements in a system. However, this approach is not precise enough because it's not precise enough to represent the complex nature inside. Therefore, many psychology researchers have proposed to use formal models to build theories. These formal models usually take the form of differential equations, and all the dynamic interactions in this kind of models are clearly defined. So based on this clear description, we can do many things. We can simulate how the system evolved over time. For example, this is a diagram for a model of panic disorder. This disorder is characterized by recurrent panic attacks, which means the patient sometimes feels extremely scared, but this fear doesn't have a clear reason. These unexpected and intense emotional attacks bring great pains to the patients. The simulation here clearly shows this phenomenon. Using the language of complex systems, we can say that there are two different states in the system. So this is the normal state, characterized by a normal low level of fear. And this is the panic state, characterized by a high level of fear. So when the system transits from the normal state to the panic state, a panic attack happens. From the complex system point of view, interactions between elements in the system can create different states. These states are not explicitly defined in the model, but on the contrary, they come from the self-organization of the elements. For example, when having high heart rate makes you feel scared and that fearful emotion increases your heart rate, then your system will have a stable state where both the fear level and heart rate are high. The stability of the system, the stability of the states is important in psychology because if the maladaptive or unhealthy state of a person is stable, then his or her system is more likely to be here, and he or she will have a mental disorder. However, if we can stabilize the healthy state and destabilize the unhealthy state, then the system is more likely to be here, and that means we can cure the patient. So that is also the ultimate goal for psychotherapies. Previous researchers often use this potential landscape metaphor to illustrate the stability of the system. So the system is just like a ball on the landscape. It always tends to go to the lower place, and when it is in the lower place, it is more stable. But how do we quantitatively know the stability of different states? Well, the current situation is that we have the formula, we have the simulation results, but we don't have a quantitative landscape for the whole system. So we don't know exactly how stable these states are. And this is the problem we want to solve in this study. We want to compute a potential landscape for psychological systems. So in order to do that, the first thing we do is to compare how the potential landscape is originally defined and how we construct dynamic systems in psychology. The potential landscape or potential function is originally defined from conservative fields. That means the force on an object in this field is proportional to the gradient of the landscape function. The dynamic functions in psychological formal models, on the other hand, are described by a set of stochastic differential equations. So is it possible to just combine them together and directly solve out the potential function? Well, unfortunately, in most cases, this equation is not directly solvable because each dynamic interaction in the right-hand side is from some theoretical considerations. They are in rather complex forms and not from a conservative field, so they cannot be represented in such an easy way. Therefore, we need to find other methods in order to do that. The method we found was originally proposed by Wang and his colleagues in the field of chemical dynamics. However, it can also be applicable for psychological systems. The basic idea is from the Boltzmann distribution, that the probability distribution is proportional to e to the minus u power. For stochastic differential equations, we can calculate its steady-state distribution, which means the collective distribution in the phase space that doesn't change over time. Then we can plug that in this question to get the potential landscape. This method is basically a generalization of the original definition of potential function, so it cannot capture all the dynamics of the system either. However, what it can do is that it can still provide information about the stability of the system, as well as the transition barrier. So what we did is to apply this idea to our psychological system. Here is the basic workflow. First, we adjust the original model a little bit to make it more suitable for the following calculation. Then, because analytically solving the steady-state distribution is too difficult for our example system, we use a numeric way, which is Monte Carlo simulation, to do this. Finally, after getting an estimation of the steady-state distribution, we obtain the landscape based on this equation. In order to illustrate the method, we use the panic disorder model by Robina and his colleagues as an example. The basic idea of this model is that the panic disorder comes from the vicious circle of physical arousal and perceived threat. The people with panic disorder often tend to overinterpret the physical arousal as an indicator of danger. So with a small noise, the physical arousal and perception begins to amplify each other. This makes panic attacks appear over and over again. The degree of this overinterpretation is given by a variable called arousal schema. So when the arousal schema is higher, this overinterpretation is more severe. We applied this method to the model and got the landscape of the system. The original landscape is in a very high dimensional space, which is not directly understandable. So we will use some marginal distribution to draw our inferences. First, this is the univariate landscape of fear. As we can see in the graph, there are two stable states of fear. The left one is the normal state, and the right one is the panic state. Both ones are locally stable, but the normal state is more stable than the panic state. This is also consistent with our theoretical predictions. And if we make a bivariate landscape of arousal and perceived threat, we can also see the two stable states. This is a 3D graph, so we can see it rotating like this. Moreover, the two variables are highly coordinated. So if one is higher, then the other one is also tend to be higher, and vice versa. So together, they make a valley here in the landscape with two locally stable points. The things above are all somehow expected from the original theory. But if we make a landscape for other variables, we can see something new. Here is the landscape of fear and escape behavior. In this landscape plot, we can also see the two stable states. But right in the middle of the valley, there is a small hill. This indicates a possible bifurcation phenomenon. And we suspect it is because the way from panic state to the normal state and the reversed way are not totally the same. So in other words, the processes of phase transition is not strictly reversible. Finally, we can also examine how the landscape changes with parameters. As we mentioned just now, the arousal schema can control the relationship between physical arousal and the perceived threat. So it is also likely to control the landscape of the system. Therefore, we made an animation to show how the potential landscape changes over arousal schema. As you can see here, when the arousal schema is low, there is only one stable state, namely the normal state, just like the case now. Yeah. But as the arousal schema becomes larger, the second stable state appears here, which is the panic state, and this state becomes more and more stable. So in summary, our take-home messages are that it is possible to make a potential landscape for the complex psychological systems. And with the help of it, we can quantitatively calculate the stability of different psychological states. We can get additional insights and inferences from the formal models, which are not directly obvious or observable from the simulation results. And we can also examine how the stability of the states changes with the control parameters. Having potential landscape in our toolbox, we can make better use of formal models in psychology and expand their inference potential. So that's all for this presentation. If you have any ideas or suggestions later, you can reach me through email or Twitter. You can also find the slides in this link. Thanks for your attention and welcome to your suggestions and questions. Thanks.
Okay, thank you very much. Very nice and on time presentation. I think we have from Felix, we have a remark from Felix. Felix?
No, that was from before. That's from the talk before.
Oh, okay, but it's on the bottom of the chat. I didn't see it. So you want to comment this presentation, no?
No, I commented the presentation before.
Okay. So some other comments or questions? Somebody has.
I have a question. Thanks for a very nice talk. One thing I was wondering about, you said that you changed the model a bit to be able to do this.
Yeah.
How much did you change it? Did you really change the behavior as well? Is it needed, or is it really like a minor change that did not change the behavior of the model in any substantial way?
Well, I think there are generally minor changes, but the most significant change is that we add some noise to all the variables. So in the original model, there is only one noise term. So that, but in order to do this calculation, we need to make sure that the system can go over all the possible states. So we need to add some noise to make sure that it can travel across all the places. And another thing we did is that we, I think we eliminated the short and long term differences. So we let all the variable changes for every step, because in this calculation, the time is not really important here, but what we want to know is the stability of different states. So these are basically what we did to the model. But generally, we checked that the model performance is generally the same as the original model.
Okay.
Thank you.
There are no more questions. May I ask you one quick question at the end? Actually, you have enough parameters to have nice pictures of the landscape. I appreciate that. But you know, when you are talking about panic, it's emotional state, and you only use arousal as a variable, okay? I imagine that because, you know, on the circle of emotions, actually, this is high arousal and small negative elements, right?
Mm-hmm.
But my question is actually, before panic, a person has normal emotions, and valence can be much different, right?
Yeah.
Do you have place in your model to introduce valence and fluctuations of valence? How it narrows close to zero in the panic state? And probably it would be useful, then your model will be much more useful to, you know, to relieve the situation if you introduce the valence. Valence is one, you know, people probably know.
Yeah,
how you can say also. It's are the emotions positive or negative?
Yeah, I know that.
Okay.
Yeah, so I think,
you know, I'm just explaining to the others. So okay, please can you answer it quickly?
a quick answer is that that would be a question for constructing the original former models. But what we do is based on that model to construct the landscape of that. So in order to do that, that's more likely in the previous step of work. It's not in the current step. But what you say is very very nice point. I think the reason that the original authors didn't include that in the model is because only one type of disorder is of interest in the primary work, and maybe in the future we will try to include all other kind of variables. But now the major point is to first build a model that can explain the panic attack, this specific phenomena. So yes, you are right, and in the future, I think it's also.
Yeah, think about this. Yeah. Okay, thank you very much again, and we move to the last presentation. If Hiroki is here?
Yes, I'm here.
Great, okay.
Thank you for staying up all the way to the end.
Soyama will tell us about information and disagreement, how these two things.
Yes, so I'm going to present by using a recorded talk. So I hope you can see my screen. Let me know if you don't hear the audio.
We hear, I hear.
Okay, everything fine, Hiroki, everything fine.
Thank you. Let me play that.
Please.
Hi, everyone. Thank you for being here. I'm Hiroki. This talk is about development of mathematical models to explain how the social disagreements may get intensified spontaneously based on some self-organizing dynamics. So this was about the recently published paper in PRE back in July. And you can download the whole material from this link. It's open access. So the basic motivation and the phenomenon we want to model and understand is how the disagreement between the people in the society can get widened spontaneously based on the interactions. So here are some examples, such as the political disagreement in the US between two parties, or defend or defund the police, that kind of the argument also in the United States, and also already getting classic, but in the UK, there was a Brexit stuff that took place several years ago. So To understand these expanding disagreement, the typical way of explaining those would be to attribute the cause to the certain kind of events or triggers or individuals, groups, to blame them because of them. This happened or that happened. But in this the study, we want to avoid attributing the causes of the growing disagreement to certain external events, but instead, can we attribute the main mechanisms of such self-organization of disagreement into some internal information sharing behavior of people? So in that case, we are trying to understand this process as a spontaneous pattern formation process, self-organization process of complex systems. So in particular, in this specific mathematical modeling work, we want to pay attention to the enhanced information gathering ability that the people have gained over the last several decades, like smartphones and the social media and the expanded computational abilities. People have more access to the wider variety of information. And how can this affect the advancement of technology by itself could explain, at least partially, the growing disagreement. So main research objective is to develop the partial differential equation-based model of opinion dynamics process. In this case, we use a lot of mathematical biology, population dynamics type of ideas to develop a model. The model itself is very simple. And one mathematical technical novelty is to use non-local gradient. Instead of just assuming that people have the access to the local gradient of the popularity of opinions, we define the non-local interaction kernel, and then the shape and the width of the kernel is being used as a model of the people's information gathering ability. And we did both the analytical and the numerical the studies to find out the conditions in which the spontaneous pattern formation happened. And then we also measured the characteristic distance between the opinionated groups and how that distance actually changes as you change the shape and the size of the interaction kernel. So that's the main objective. Here's a model. A model is very simple. It's a transport equation with diffusion terms and the non-diffusion based more active aggregation process. The first term is the diffusion term, and the second term is the chemotactic behavior. So population actually moves toward the higher peak of the perceived population density. So this is the opinion space. For simplicity, we assume the one-dimensional continuous finite line segment as opinion space. And the population density is represented as a function P of X and T. And the assumption here is that the people are more like a homophilic individuals. So they want to move their opinions more toward the popular ideas. So they want to assimilate local neighbors. So in this case, we use this non-local interaction kernel, this sine wave-ish curve. So you calculate the cross correlation between the population distribution and the local perception kernel. In this case, it's negatively correlated, so value is going to be negative. Therefore, individuals standing on top of this point will tend to move toward the left, which naturally follows the slope of the population density at the local scale. So the peaks get higher, valleys get lower. So that's the highly unstable dynamical process. And this one, as I mentioned, this model uses non-local interaction kernel. The kernel is defined here, lowercase g, and this is the cross correlation between the population density P and the local interaction kernel G. So kernel is defined as a combination of two Gaussian curves, one on the right for the positive side, another on the negative side for negative the amplitude. So this is the exact shape. And by changing the distance between those two peaks and also the width of each of the Gaussian kernel, we can change several different scenarios like this, as pictured in this slide. So as you decrease the distance mu and the standard deviation sigma toward 0, we can mathematically prove that this actually converges to original local gradient. And as you keep increasing the sigma and the mu to the larger value, you represent the situation where people have access to the wider variety of information. So the main objective is what's going to happen if you change the sigma and mu. So here's one demonstration. So as you start the simulation from the locally, globally homogeneous yet with minor perturbation added state, you eventually see this kind of self-organization process. And this is fairly commonly known in mathematical biology. It's an auto-aggregation process. The peaks get higher and the valleys get lower and eventually reaches population zero. And you see these distinct population sites. So in this case, you can measure the characteristic distance between peaks, and that gives you the quantitative idea how much disagreement exists between opinionated populations. And here's more a spatial temporal visualization of the same results. It's a space-time visualization. Horizontal axis is space, opinion space. Vertical axis is time, flowing from bottom to the top. You see at a certain point in time, the spontaneous pattern formation gets established. And once you see the opinionated population here and there, they are fairly stable. Sometimes you see the merger between opinions here. And this is fairly generic pattern formation process in this model. And we conducted the linear stability analysis. What kind of wavelength would be able to destabilize homogeneous solutions. So without all the mathematical details skipped, you can take a look at the original paper. So here's the final conclusion of linear stability analysis. And then you can show that if this big quantity is positive for a certain spatial frequency omega, the homogeneous population density distribution is unstable. And we can rewrite a little bit so that by defining this function as a Q of omega, you can show that if the people's tendency to move toward the locally more popular population, that's the parameter C, and the population density P of H is greater than diffusion terms, diffusion constant, then the pattern formation happens. So this is fairly consistent with any other mathematical biology type of models. So the main question here then is, what would be the effect of this interaction kernel to satisfy this inequality, to destabilize the process? So we did a numerical calculation of this quantity Q of omega for different value of omega and mu and sigma. So simply put, as this mu and sigma becomes larger, which means that the people gain more and more information from a wider source of opinions, the characteristic spatial frequency omega gets smaller, which means that the distance between peaks gets larger, longer. So therefore, this qualitatively shows that as the people have access to the wider opinion space, then the people's disagreement actually gets much, much bigger. So here's a numerical simulation that shows the actual patterns as you increase sigma, standard deviation of Gaussian kernel, and mu, the distance between two different Gaussian kernels. As you can easily see, greater values of sigma and mu tend to create a more and more distant, much larger population spots in the space. And here's yet another visualization, the summary of all the numerical solutions and analytical calculation together. So blue dots are numerical simulations and showing that specific value of mu and sigma and the characteristic distance between peaks in the opinion space. And all the numerical simulations are always above the analytically predicted lower bound. So this guarantees that as you increase the parameters mu and sigma, the population peaks needs to get farther away. So this confirms our initial hypothesis that people's information gathering ability may actually contribute to the more disagreeing opinions. So we can use, in the last 1 minute, we can also run some scenario simulation. So this is a simulation with temporally increasing value of sigma and mu. So you can set up the initial condition like this. Initially, you have some opinion groups already established. And as you keep increasing sigma and mu during the simulation, this happens. So this would be the interesting illustration of what might have happened over the last 5 decades in the human society as people get more and more access to the faster computation
and more efficient information gathering ability, opinions get merged, and eventually you have a very extremely disagreeing the major opinion groups. This is a very suggestive to what's happening maybe. And also we also tested another scenario. Can we stop that kind of trend by suppressing social media, for example? So this is another simulation that changes the value of sigma and the mu in the middle of the simulation. And turns out you cannot reverse the directions. Once the opinion groups are established, even reducing the sigma mu does not really reduce the disagreement. So instead, they get crystallized. So this gives us another challenge. What else can we do to diffuse those opinionated groups? So this is not a simple question to answer. Anyway, so that's it. So conclusion is this study illustrated how the increasing ability of information gathering might contribute to the widening disagreement in our society. And the external intervention we tested at the very end may not help relieving that kind of conflicts. So one main paradox here is that our models show that the more information people have access to, the more severe their disagreement can get. So this is quite counterintuitive. So we want to thank our funding agency, JSP Skakenki, and the Max Planck Institute in Germany. Thank you very much. This is the picture I took from the Dresden when I worked on this project.
Okay.
Thank you very much.
Thank you. Thank you very nice. Very nice.
Thank you very much.
And we have time for one question, maybe. Somebody wants to put question or comment. We all have opinions about this, right?
Yeah.
Well,
I'll be happy to take any questions.
So just one very quick comment.
Yep.
You remember the message from one of the message from Professor Levin's talk today?
Mm-hmm.
Maybe everybody remembers that the advanced technology will change cooperation and how. I think you went a step forward and showed how it is happening.
Yep.
So it's a very nice message for today, for me at least.
Thank you very much.
So there are no more questions. So somebody has a comment here. You can read it. Okay. So we should close the session.
Yep.
Yeah, we're almost done for the day. Yeah.
Yep. Thank you very much, everyone.
They had so many nice talks in this and
yes, indeed.
This late hour, and very interesting even for us physicists. Spanish and me.
Okay.
So thank you all. I finished this.
Okay, so we close the Zoom room in the next 1 minute and continue tomorrow.
Okay. Thank you very much.
Okay. Take care, everyone. Take care. Bye.